And here we are to wrap up chapter 3. Kind of like we opened the chapter, it was broken into two sections, an A and B. We're going to do that also here, dealing with the hydrosphere and biosphere. And it doesn't break up quite as nice and neat as just the hydro and then the bio, but here we go. So section 3A, once again, two sets of Cornell notes here. I'm going to run through it all in one video, but two sets of Cornell notes. As always, watch the video, have the PowerPoint open on another window or another device if at all possible. And here we go. Your essential question. What is the primary relationship between the water cycle and the ocean? Not really something you could probably do off the top of your head, but let's see. The hydrosphere, first key term. The hydrosphere is just going to include all the water on or near the Earth's surface. So water in the oceans, on the lakes, rivers, wetlands, the polar ice caps, in the soil, sunken down in where plants are taking it out, under the rock layers, and even in the clouds. So water, anywhere we find it on the planet Earth, makes up our hydrosphere, which takes us pretty much right into the water cycle. I'm not going to spend a lot of time here because most of you should have this down pretty solid. It's just the continual movement of water from the ocean to the atmosphere to the land and back into the ocean. Evaporation, the changing of a liquid into a gas. Water is continuously evaporating from the Earth's oceans, along with lake streams and even puddles, but the majority of it is happening from the ocean. The ocean covers 71% of the planet Earth, and 97% of all water on the Earth at any point in time is in the ocean. So it is our main source. Yes, it's evaporating from a puddle, but not near the rate that it is evaporating out from the ocean, obviously. So we have evaporation. Warm air then rises. As it travels up in the troposphere, the temperature comes down. So that warm air rises, it cools, condenses, and it then changes from a gas. Enough water droplets get together to form a liquid, and then it will precipitate, fall out of the sky. Normally in the form of rain, but it can be snow, sleet, hail, any form that the water forms into and falls from the sky. Now it normally forms on droplets of dust that then form up in the clouds. So typically what happens is a water molecule finds something to settle on. It's not always just water finding another water molecule. It can happen, but typically little other particles of dust, carbon that are up in the air, and they collide and then they get heavier droplets and eventually falls. But usually the combination of dust is a big key for it to begin to condense and then fall out of the sky in the form of precipitation. And this is my favorite picture graph of the water cycle. I know it might be a little too elementary schoolish, but it's, the sun's evaporating a little, carrying them up into the sky and then letting them slide and fall back down into the planet Earth. But cute picture, but it pretty much wraps up the water cycle. And this takes us to the Earth's oceans. Give me a second, let me grab my globe. All right, the Earth's oceans. Now, all of the Earth's oceans are actually joined into one interconnected body of water. So we talk about it in terms of Pacific Ocean, Atlantic Ocean, but in reality, it's all one body of water. We just break it down into different names to make it a little easier to reference. Let's start off with the largest, the Pacific. Now, the Pacific Ocean covers about an entire third of the planet. From this particular view, it almost looks like the whole planet from what we can see. But this is our largest ocean. Now, when I talk about the oceans, make sure you can kind of give me their relative size, at least compared to one of the other. I'm not going to nitpick you on the surface area. I know that's in there as part of the notes, but definitely know which one's the biggest and know a couple of features about the Pacific Ocean. The deepest point in the Pacific Ocean is right off of the Philippines, and it is the Challenger Deep. It's located just off the Philippine Islands, and it's the bottom of the Marianas Trench. So the whole Marianas Trench, but the Challenger Deep is the deepest part of that. It is some 11 kilometers below sea level, which would be deeper than Mount Everest is tall. Mount Everest is like 8,000, almost 9 kilometers tall. Challenger Deep, 11 kilometers deep. So it is our deepest one by far. Now, a lot of times we will, oceanographers at least, will divide the Pacific Ocean into the Northern Pacific and the Southern Pacific based on the ocean currents. Just one, but they'll often refer to it in these ways. Now, surface currents. Surface currents are driven by wind patterns. And what happens is, here's the equator. What happens is in the northern hemisphere, we tend to get a clockwise current, and in the southern hemisphere, we get a counterclockwise current. We'll look at this later on in the chapter, but for now, you just need to remember, northern currents run clockwise, and if I come over to the Atlantic, it helps because our jet stream. They go clockwise in the northern hemisphere, and they go counterclockwise in the southern hemisphere. So sometimes we will talk about the North and South Pacific. It's really all one, but that's why. And know which way the currents go. Clockwise in the north, counterclockwise in the south. Now we're going to rotate around and go to the second largest ocean. This is going to be the Atlantic. Now it's only about half the size of the Pacific. And just like the Pacific, it can be divided into a northern and a southern. Once again, clockwise, counterclockwise in their currents. Then we go over to the Indian Ocean. So here's India, just below it. Now it's a large ocean, but obviously there's only this one ocean. There's not a northern section to it. So it's very close to the size of the Atlantic. It's this whole area. But that's kind of its feature. It's going to have this one current here, doesn't have a north. The Arctic Ocean, up at the top, is very unique because it's typically covered in pack ice. Now, this globe doesn't show it. It's kind of like the little metal part on top would be a lot of this pack ice. But it's our smallest ocean by far, and its kind of unique feature is going to be this pack ice covering it because the wind and waves kind of push everything together and it freezes up. In the summer months it breaks up, but then through the winter you get this hard solid ice pack pretty much up near the top. Ocean water, fresh water. The difference between it is just salinity. Ocean water has more salts in it because any salts that make it. Now our fresh water has some salt. It's just not very salty. It's very, very little amount. So any salts that make it into our fresh water pour out and go into the ocean, and there they remain because the water cycle is evaporating only water and the salts remain. So any amount of salt that makes it into our fresh water runs into the sea and the salts accumulate there. So over time, the ocean has become salty. Now salts come out from you and me. Our sweat is salty. Sweat makes it to the ground. An animal dies. The blood goes into the ground. All this eventually washes its way into the streams and then down into the ocean, and the salts and the minerals remain there. Now salinity is lower in some places. If you happen to be a creature that lives in the sea and you live near the shoreline, well, when it rains, it's not as salty as if it's not raining. So animals close to the shore have to deal with different levels of salinity, and areas where the water evaporates rapidly may actually be more salty. So the ocean is not a uniform saltiness. Some areas of it are more saline, has a higher salinity than others. Just understand there's a mix and you'll be good. Now let's look at some of the things that are in it. Most of the salt is just sodium chloride. You see where chloride is like 55%, sodium is about 30%. Now this is not the ocean, this is just minerals that we find in the ocean. Most of the ocean is going to be H2O, so we're only talking about minerals that we find there. But primarily what we find is sodium and chloride. Although there are a lot of elements there, a lot of other minerals, magnesium, sulfur, calcium, potassium, etc., all can be found in it. So if you're getting sea salt that we're doing out, most of it's going to be sodium chloride, but there will be some other minerals in there. Typically, it just depends on what part of the ocean the salts came from. Let's talk about temperature zones. The ocean is huge and it can be quite deep. For you and I, we go around the shoreline and it's not very deep. And even if you get a mile offshore, the ocean is rarely much more than, say, a mile deep. But you get out in some areas, and all the ocean is maybe 2, even 3 miles in its depth. So there's this huge depth of the ocean. So the ocean's getting warmed by the sun, solar radiation hitting the water, warming it up by radiation. And then the depths of the ocean, where sunlight doesn't reach, are very cold. Now, if you've ever gone to a lake and you're swimming around in summertime and you kind of dive down, you go down 10, 15 feet and all of a sudden it gets cold and you can feel this quick temperature change. Well, that's the same type of thing we're referring to in the ocean. Now, the surface waters get stirred up by waves and currents. The surface zone can be as deep as 350 meters, 3 to 4 football fields deep is all a very similar temperature. Now, there'll be a very distinct one just a few feet down, but once you get down 10 meters, that temperature stays fairly constant. So for about 300 meters, give take, the surface temperature is fairly warm. And then below that is what we call the thermocline. So I'll throw the picture up here as I begin to talk about it and go through. So the surface temperature is around 300, 350 meters, and then between about 300 to 700 meters, so about the same width of band, is the thermocline. And here the temperature drops rapidly. It goes from around 20 to 23 degrees Celsius in only a few hundred meters down to about 5 degrees Celsius. And then it only goes from 5 or 6 degrees Celsius down to about 4 degrees Celsius at the deep bottom. So we have a warm layer, a rapidly declining temperature in the thermocline, and then I have a always cold and dark. So the surface layer gets a lot of sunlight. The thermocline, not very much. It's pretty much dark, but it's a twilight zone, if you will. And the deep zone, no light ever reaches it, and it stays very cold. So we'll refer to this thermocline in different instances because it's an important factor in life zones as well. That'll take us through our first section of the notes. So get out a new set of Cornell note sheets if you're taking your notes from it. And here we have section 3B. Still of the hydrosphere and biosphere. We have to wrap a little bit up about hydrosphere and then we'll dive into the biosphere. Well, here's my question for you. Your essential question: explain how the ocean regulates Earth's temperature. One of the most important functions of the ocean outside of the water cycle and a place for animals that live is that it absorbs and stores energy. 71% of the Earth is ocean. The sunlight is hitting the ocean 24/7, right? It's not hitting the Pacific 24/7, but it's hitting one of these bodies of water, which are all interconnected all of the time. So it's absorbing all of this energy, and then the currents are carrying that energy around to different places on the planet. Since the ocean absorbs energy and it releases it slower than land, the temperature changes more slowly. On land, like we use an example, you go out in the morning, the asphalt's cool. You go in the afternoon, it's really hot. You go out in the evening, it's cool again. That doesn't happen with water. You go in the water and it's 78 degrees. You go in the afternoon at 78 degrees. You go in the evening at 78 degrees. A month later, it might be 79 degrees. It takes it a long time to warm up, but it also takes it a long time to cool down. So it can regulate that heat. It absorbs heat slower and it releases it slower. So it warms up around the tropics and it carries that heat from the tropics all the way up, say in our case, coast of Florida, South Carolina, North Carolina, and on up, keeping that area unseasonably warm for its latitude. If the ocean was not regulating some of this, both atmosphere, because the it's warming the air and the area near it, then once again, temperatures on the Earth would be too extreme. So it acts as a global regulator. Now, local temperatures in different areas are, let me grab my Earth again. So let's take somewhere like here. Now I'm going to follow this latitude around. So if I come over here, this puts us kind of in the middle of the United States. So in wintertime, it's going to be fairly cool and cold. And here is the line of upper United States. We associate this with being really cold. I'm moving here up into Canada. And this area of Canada is almost getting just below the Arctic Circle. Well, if I come straight around to here, I run into England. Now, England has some snow in the winter, but very few. Why? Because it's an island nation and the warm ocean currents are carrying up and then down through here. The ocean keeps England unseasonably warm. If I track England all the way across, well, I'm in Siberia. Siberia is frozen wasteland because it's inland, not near the ocean. England stays fairly temperate. When I get over here into Canada, very cold. So our oceans will keep certain areas warmer than we would expect them to be. Ocean is a regulator of heat. Warms up slowly, releases the energy slowly, and it keeps some places unseasonably warm. Anywhere that tends to be near a coastline has to have more moderate temperatures. These surface currents we talked about, in the northern hemisphere they go clockwise, and in the southern hemisphere they go counterclockwise, but they're driven by these global wind patterns. So the surface currents can be warm or cold water currents, just depends on where it's coming from. If it's coming down from the Arctic area, it tends to cool off. But interestingly enough, warm water and cold water don't readily mix with each other. Take a look at this. That's an actual picture where a warm water current, the dark blue, is meeting a cold water current, the kind of light greenish color. And they don't mix well. They will eventually, but the two come in contact and the warm water tends to drift up over them. Remember, warm water will rise, cold water will sink. The cold water tends to go under it and the warm on top, and it takes a while for the two to blend into each other. So when we have cold water and warm water coming in contact with each other, they don't mix well. They will over time, but that line stays there almost constantly. Then we have deep currents. So we've talked about surface currents. It keeps the area above the thermocline warm because it's all churning and moving around, but we also have what we call very deep currents. These are stream-like movements that flow very slowly along the ocean floor. So as the water cools off, like up near the poles, it gets cold. Cold water is denser than warm water, so it sinks. And if it's saltier, the more salt in water is also denser. So if we get salty and cold water, it begins to sink. And it kind of sinks down at the poles and begins to move across. So it gets cold at the poles, and that water sinks to the very bottom of the ocean and slowly makes its way towards the equator, and then it will pull back up as it warms up as part of a cycle of water under this. So we have currents on top, but we also have a deep current that moves very slowly underneath, right on the bottom of the ocean, and it moves from here to there. The coldest and densest one is from Antarctica. It travels down deep, moving its way towards the equator in these little rivers of movements deep on the ocean floor. This will take us to freshwater. Lakes and river systems largely. Freshwater is just insignificant amounts of salts. There'll be small amounts of salt in freshwater, but it gets carried down to the sea where those salts get stuck and the ocean slowly gets saltier and saltier. So freshwater, insignificant amount, very small. Most of the fresh water, however, is locked up in ice caps and glaciers at any point in time. The ocean is 97% of water, but when we talk about only fresh water, most of it, over 90%, is trapped in ice at any given time. There's just a lot of ice at the poles and leaves very little, if you will, to flow into the lakes, the rivers, the wetlands. So, groundwater. Groundwater is just what it sounds, water on the ground. Now, most of this is trickling down. Rain hits the ground, snow melts, etc., and then it runs off into the land. This makes up only 1%. So we're talking groundwater. This is like I can walk up to it and stick my toes in it. Basically a lake, river, stream, or a wetland. Only 1% of water on the earth is groundwater that we can get. But this fulfills our need for drinking water and supplies our agricultural, industrial needs by and large. So the ocean is the largest part, fresh water, very small amount, and the groundwater, once again, what we can just easily access is only 1% of the water, very small amounts. And this takes us to the biosphere, where life exists. About 12 kilometers down into the ocean. Marianas Trench is 11, but anyway, about 11 kilometers down and about 9 kilometers up. So you're looking at a 20-kilometer range where life exists. Pretty narrow band. Now, the materials that an organism require have to be continuously recycled, like water, like air. And gravity allows it to maintain the atmosphere and to cycle these materials. So suitable combinations that organisms need to survive are only in this biosphere. So gravity's pulling the atmosphere down, but enough oxygen to live on is only in a pretty narrow band, maybe about 9 kilometers up. We have breathable atmosphere by living things, by life, and then it only dissolves down into the ocean. So I get this little narrow band because I'm dependent on the cycling of nutrients. So it's near the surface as well because that's where the sunlight is. Plants, as we know, require sunlight to produce their food. They're autotrophs or producers. They produce their own food by energy from the sun. So they're dependent on sunlight reaching them. Deep down in the ocean, we don't have any plant life. The things that survive there are often things that are dying and drifting down. So plants, which is the base of all of our food chains, require sunlight, and most things require enough either oxygen or carbon dioxide to cycle the nutrients. So we get this kind of narrow band, only so far up into the troposphere and down into the water. And most of the ocean, or most of the algae in the ocean are floating in a form of plankton, and they kind of can swim up and down, but they just drift with the currents. Now, the energy required by organisms has to be obtained in this biosphere, and they have to constantly be resupplied. Once again, typically, the bottom of the food chain is going to be autotrophs, producers, plants, if you will. And then when an organism dies, its body gets broken down into the nutrients that everything needs. So typically you have a plant, something eats the plant, something eats the thing that ate the plant, something eats the thing that eats it. It dies, and then the decomposers break it down, and the nutrients go back down into the soils, into the water, where the plants extract the minerals they need for life. And it's this flow of energy that allows life on Earth to exist. This constant cycling of nutrients throughout the planet. Now, this energy flow can be talked about in terms of a closed system and an open system. A closed system, matter cannot be exchanged. Matter can't come in, matter can't go out. Earth, right now, is essentially a closed system. Nothing comes in, nothing goes out. And I always say, yes, a meteor comes. That's like dust landing on my back. If I go to weigh myself on the scales, I'm not concerned with the dust because a little bit of dust lands on me and some skin cells fleck off. That's about what it's like to the Earth. Almost nothing comes in and almost nothing leaves. It's very, very tiny amounts. So concerning matter, Earth is a closed system. Nothing comes in, nothing comes out. If it's not here, we don't have it. But in regards to energy, it's an open system. Energy does come in from the sun. Sunlight and heat come in from the sun, and heat escapes from the earth. So the earth, in regards to matter, we're closed. Nothing comes in, nothing goes out. In regards to energy, we're open. And many systems can be like this. It's very difficult to have a system that's truly closed, that no energy comes in or goes out, just for the heat. But normally we talk about things as with matter, they can be closed, but with energy, they tend to stay open. But a truly open system, both things come in and out. Like I have a potted plant. Well, I'm adding water into it, water is escaping, I'm adding matter in the form of water, water evaporates and grows out. So a potted plant is an open system. Energy's coming in, energy's going out. Matter's coming in, matter's going out. But in the form of a terrarium, like our project, it's a closed system. Nothing else is getting in once we sealed it except energy. So make sure with an open and closed system, you understand what we're referring to and that things can be both or only one, given the proper circumstance. That wraps it up for chapter 3, guys. Take care. We'll see you next time.